Bismillahirrahmanirrahim. In this video lecture, we will have a look through sequence circuit for delta Y transformers. Like in our last lecture, we discussed about the sequence network for the synchronous machine or rotating part of the power system. So here in this lecture, we will see the sequence circuit for the transformers. Let's start with some basic. So actually in power system we have a large number of three-phase transformers. And what are three-phase transformers? These are three identical single-phase transformer connected in delta and Y configuration, and based on this configuration we call them delta Y or Y delta configuration or YY or delta delta configuration. A transformer can be presented by their equivalent circuit, and for each equivalent circuit we will be having three symmetrical components: the positive sequence component, the negative sequence component, and the zero sequence component. However, the winding configuration can be seen only in the zero configuration or the zero sequence component. The Y connection, delta connection, grounded, ungrounded, these configuration can be seen in the zero sequence component. So we will have a look through the zero sequence component of delta Y, Y delta, delta delta, YY transformers. So let's start with the first case. If we have YY bank or YY transformers and both the neutrals are grounded, this will be the symbol: Y connection, grounded, grounded. Primary side is grounded, secondary side is grounded, and the connection is YY. So in this case, if we want to draw the equivalent circuit, we will be having Z plus 3Zn for the primary side, and similarly for the secondary side we will be having some 3Zn for the secondary side. And if we want to transfer the 3Zn of the secondary side to the primary side, we have to multiply it with the turn ratio. So the total zero sequence circuit will be some circuit with some reference bus and some impedance, zero sequence impedance, and the zero sequence impedance will be equal to the Z, the zero sequence impedance, the neutral of the primary side plus the neutral impedance of the secondary side. And if we have the N1 by N2, the turns ratio is 1, then we will be having Z plus 3 Zn plus 3Zn. This case is for when both the connection are YY and the neutrals are grounded. Both connection are YY and the neutral are grounded. So the equivalent circuit will be looking, simple equivalent circuit will look like this, and the impedance will be equal to Z plus 3Zn plus 3Zn. Similarly, if we have YY configuration and one neutral is grounded, one neutral is not grounded. So if we have for the primary side, we will be having for the IA, we will be having the positive, the zero sequence, the positive sequence, and the negative sequence current. Similarly for the IB, we will be having IB for the zero sequence, for the positive sequence, for the negative sequence. For the IC, we will be having the zero sequence current, the positive sequence current, and the negative sequence current. Similarly on the secondary side, for IA, IB, and IC, we will be having the positive sequence, negative sequence, and the positive sequence, negative sequence, and the zero sequence component. And if we want to look at the equivalent circuit or representation, that case we will be having some open circuit. Open circuit because if either of the neutral is ungrounded, if this neutral is ungrounded or if the secondary side neutral is ungrounded, the sequent current cannot flow. The sequent current cannot flow, and the Zin will be equal to infinity, and there will be no path. There will be absence of path for the zero sequence current to flow between the two parts. So we will represent this through some open circuit. Case 3, when we have delta connection and both the sequence are in delta connection with no ground configuration, again we will be having for the IA, IB and IC, we will be having the positive sequence component, the negative sequence component and the zero sequence component. Similarly for the secondary side, we will have the positive sequence component, the negative sequence component and the zero sequence component. And if we want to show this through some equivalent zero sequence circuit, as there is no path for the zero sequence current to flow, so both the circuit, the primary side and the secondary side will be shown through some open circuit. The IA0 and the IA from the primary side and the secondary side, the capital shows the primary side while the small letter shows the secondary side. Both will be equal to 0. Case 4, when we have the Y delta bank and the Y is grounded. The Y is grounded and the delta is not grounded. In that case, first we will be having some positive negative sequence and zero sequence current on the primary side and similarly on the secondary side with some turn ratio N1 and N2. And if we want to see what will be the relation of the VA, the voltage of the zero sequence, so it will be equal to N1 by N2 VB, the turn ratio, plus 3Zn into IA, or we can say VA minus 3Zn is equal to N1 by N2 VAB, and the Zn is on the high voltage side or on the primary voltage side. And if we want to see the zero equivalent circuit, so for the high voltage side we are having Z plus 3Zn, while for the low voltage side we don't have any path. Case 5, when the Y and delta banks both are ungrounded. So if both are ungrounded, we will be having the equivalent circuit with no path to flow the current. So we will be having Z plus 3Zn, and similarly here some open circuit. In case 5, if we have the positive sequence current, the IA, so the IA will be what? Will be having the VA on the high voltage side, it will be equal to the voltage on the low voltage side with some 30-degree phase shift. This we already discussed in great detail when we were discussing about the ideal and the practical transformer, that in case of the transformation we have some 30-degree phase shift, and similarly in case of the negative we again have some 30-degree phase shift. And for example, if we have some power system, some one line diagram per power system which have a number of transformers with configuration Y delta or delta Y configuration, and the primary side, the high voltage side, is grounded or ungrounded. In that case, if we want to find the equivalent circuit, we have to recall these cases. Like in this case, both are ungrounded, it is case 5. When the secondary side is grounded, it is case 4. And similarly, when the higher voltage side is grounded, it is case 4. And same is if we combine all these circuit. If we combine the case 4, case 3 and case 4, we can get some total circuit with some total configuration. The case 4, the case 5 and the case 3, we can combine all these 3 together. And similarly, if we have, this is an example, I would like you all to do this by yourself. Like in here we have again the delta and Y configuration. Similarly here the YY, but Y is grounded, so you all need to recall the cases, the case 2, the case 1, the case 3, case 4, case 5. Similarly, we don't have case 5 in this case. So and then you have to sketch them and draw the total equivalent circuit. Or we can summarize all these. If we have all the discussion, we can summarize in this form. Both are ungrounded, so both are open. One is grounded, so one is grounded, one is open. Both are grounded, both are connected. Similarly, both are ungrounded. Here one is grounded and here both are ungrounded, so both are open. So in this we can configure this in this slide or in the previous slide. These both configuration are of the same circuit for the positive for the zero sequence network. When one is grounded, so one is grounded here, both are grounded, so the total circuit. One is grounded, one is ungrounded, one is grounded, one is ungrounded. Similarly, again one is grounded, one is ungrounded, and similarly both are ungrounded. We can summarize this for the positive sequence network, similarly for the negative sequence network, and for the zero sequence network. For the zero sequence network, this form, this is already given in the book, and we already discussed this form of equation or this form of the transformer representation in our chapter when we were talking about the transformers. This example is very important for you to understand the concept of the sequence network for the transformers. In this example, we have a 75 kVA transformer. A 75, this is the capacity of the transformer. The voltage on the high voltage side is delta configuration and the voltage is 480 volts. The secondary side is with low voltage configuration and the voltage is 208 volts and the configuration is Y. The transformer with a solidly grounded neutral. The neutral is solidly grounded, is connected between the source and the line as in example 8.6. So what was example 8.6? We already discussed in the first part of this lecture, and we solved in detail example 8.6. The leakage transformer reactance is 0.10 per unit. The reactance, equivalent reactance is 0.10 per unit. The winding resistance and excitation currents are neglected. So we are not worried about winding resistance and exciting current. Using the transformer rating as base quantity. Using the transformer rating as base quantities. These three ratings can be used as base quantity. Draw the per unit sequence network. We have to draw, like for synchronous, in last example we saw the per unit sequence network for synchronous machines. In this case we have to draw the per unit sequence network for the transformer and calculate the phase source current IA. Two things, per unit sequence network and the phase current IA need to be calculated. So this was example 8.6. In example 8.6 we have some synchronous machine and then we have some line impedance and then we have some load. What is in example 8.7? We added a transformer on the primary side and then we connected another transformer on the secondary side, and the load and the line impedance are the same. So this part is already discussed. We add these two parts. This part, the primary and secondary, the delta configuration and the star configuration. The delta configuration and the star configuration. This part was added. A transformer was added in between this circuit of the example 8.6 at 75 kVA transformer with 480 volts on the primary side and 208 volts with Y configuration on the secondary side. And the base quantity, if we want to base quantity, already in example we have given that use the transformer rating for the base quantity. For the single phase we divided it by 3, and similarly the V base between the higher side and the line in the neutral by √3. So the V base is 277.1 volts and the S base for the single phase is 25 kVA. Similarly, V base for the lower side is the 208 volt divided by 3, 120.7 volt, and the X base. The X base is actually we can derive by using the S base and the V base. For the Z base we can derive simply it by the X base, V base and the S base. This part we already derived this network in example 8.6, the zero sequence network. Just we convert this zero sequence values to per unit values by dividing it by the V base. Similarly, this we already derived in example 8.6. Right now we divide it by the V base and change this value into per unit value. And similarly for the V2, the negative sequence, this value we already divided it by the base value to change it to the per unit value. And similarly the zero impedance, or for the line the positive impedance or the negative impedance, all is the same, 1/85 and divide it by the base value, we change it into the per unit value. Similarly for the load Z delta divided by 3 and we divide it by 0.775 the base value to change it into the per unit value. This image is actually we change, like in our book we have the Y to delta and this is delta to Y configuration. So here this is the zero sequence the voltage in the form of per unit, the current is 0, and the equivalent reactance. Similarly, the line impedance, the load impedance, and some open circuit from the previous. And similarly for the positive sequence voltage in per unit, the equivalent, the phase shift because of the delta to Y conversion, the phase shift, and the line impedance and the load impedance. Similarly for the negative sequence network. For the negative sequence network, we have the negative sequence voltage. This voltage we already derived, just we convert this value into the per unit value, the per unit equivalent reactance, the transformer delta to Y conversion, the phase shift 30° plus in case of the positive and 30° minus in case of the negative sequence. And similarly the load, the line impedance and the load impedance. This is how you can find the positive, negative, and the zero sequence component of for the transformer. And if we want the positive sequence current, we want to calculate this current IA. If we want to calculate this IA, so we need to divide the voltage, this voltage by all these impedances. We want to find the current in this loop, the IA. So all we need, divide this voltage by the impedance, the sum of the total impedances, this one plus this one plus this one. So here V1 divided by the equivalent reactance, the line reactance, the load reactance, and this value in per unit. Similarly, if we want to find the negative sequence current, for the negative sequence current, we have to divide V2 by its equivalent reactance, line reactance, and load reactance. And then if we want to find the IA, the phase current IA, we have to add the positive sequence component, the negative sequence component, and the zero sequence component. Zero sequence component is 0, positive sequence component is 0.05326 here, plus the negative sequence component 0.00179282 here. So in the per unit, this is the IA current, and if we divide this per unit value by the I base, we calculate the I base value, the power divided by the voltage, and multiply it with the per unit value, we get the actual value 4.705 with some angle of -46.19 degree.